and he is just on inspection. Oh, really? Basically, this was what money is. Oh, thank God she did. Yeah. That's $600 she gets spent. Yeah, that's right.
Should I introduce? Should I, Steve?
Yes. Do it at 7:31.
I'm ready.
You ready?
Yeah.
Don't stand there because you got text right over your forehead.
Okay, everyone. Thanks for coming. I'm Andy Heidinger. For those who haven't seen me in a couple of years, I'm a no employee, but also Chuck's research advisor. So today, Charles White, aka Chuck, is giving his Ph.D. defense. Chuck came here in 2016 and got his master's degree with myself, Steve Ackerman, and Peter McIntyre in limnology. And he did a very, I think, impressive work as a master's student of generating his own SSTs over the Great Lakes, and studying some of the cool patterns, climatology there. And he stayed on for his PhD, and he will be, let me get this right, he will be discussing his work on applying AI techniques to a few very relevant problems in remote sensing that he's worked with me and Steve and others for years. So he'll typically give 55-minute presentation. I think he would like questions, unless they're ultimately pressing, to come at the end. So, you know, I have to admit, I'm not an AI expert, nor was his committee. So those of you that are AI experts, you know, please don't hold back. So, without further ado, Chuck. Thanks, Andy. Okay, can you all hear me in the back okay? If I talk like this? Okay, perfect.
So yeah, this is a long presentation. It comes in at around 55 minutes. So if you have a really long question, we're going to try and look at the end. But if it's something short, like what's on the y-axis, or if I use some jargon you're not familiar with, feel free to ask that. Okay, so I'm going to go ahead and get started. Satellite imagers are passive instruments that measure radiance at high spatial resolution but low spectral resolution. This is in contrast to something like a hyperspectral sounder that has high spectral resolution but low spatial resolution. There's examples of 3 imagers here, but the first of 3 we're going to talk about is VIIRS, the visible infrared imaging radiometer suite. So it's a polar orbiting imager, has 16 visible near infrared and infrared channels. The channels we care about are the 750 meter spatial resolution. It's on SUMI NPP and JPS supported satellites. The second imager is ABI, the Advanced Baseline Imager. We're probably all familiar with this. Geostationary orbit, 16 channels. The channels we care about are a 2-kilometer resolution, and it's on GOES 16, 17, and soon to be 18. The last one is MODIS, the Moderate Resolution Imaging Spectroradiometer. Also a polar orbiter, 36 channels. The ones we care about are the 1-kilometer resolution, and it's on the Aqua and Terra satellites. So why would we use these instruments to estimate properties of clouds? This is maybe not something I need to motivate for this audience, but I'll go through a few here. Navigation and aviation hazards. If I'm a pilot, I probably don't want to fly through a lot of super cool water, so this icing product tells me where that might be likely. Clear sky applications. If I want to estimate properties of the surface, like lake surface temperature or lake water turbidity, I need to know where the clouds are not, so I can be confident that my estimates are cloud-free. Solar energy nowcasting is an interesting one. If we have a solar farm, we need to know what ramps in energy production are going to occur, so we can adjust other sources of energy generation accordingly. Of course, clouds serve a significant role in Earth's energy balance. In conjunction with aerosols, they're one of the largest sources of uncertainty in future climate projections. And it's certainly not helped by the fact that there's many sources of uncertainty in our longest observational records of clouds. On the right is of Antarctic cloud fraction. These top 3 data sets here are Clara A2, CCI, and Atmos-X. All 3 of these data sets are different reprocessings of the same data from AUHRR. We see there's differences in the mean cloud fraction, the seasonal cycle, and the overall trend from all 3 of these. So there's uncertainty from an algorithmic perspective as well. As far as the kinds of things we might estimate about clouds, there's an incomplete list right here. I'll talk about each one of these. Cloud detection. For every pixel in this image, we want to know, is there or is there not a cloud? If there is a cloud, we want to know, is it one layer or are there multiple discrete layers? Once we know there's a cloud, we might ask what the phase is. Is it liquid or ice, or is it mixed phase? Is cloud top pressure, altitude, and temperature? All three of these variables are intimately linked. If we know one of these, we can usually use a background temperature profile to figure out the other two. They all give an idea of the vertical placement of clouds in the atmosphere. If we know cloud top altitude and we make an estimate of cloud base altitude, we can estimate cloud geometric thickness. That's in contrast to cloud optical thickness, which gives us a little bit of information about how much light can pass through a cloud. So the problem of cloud property estimation is essentially how we take all this information on the left, radiation measured at several different wavelengths, and use that to estimate properties of clouds we care about, like cloud fraction and cloud top pressure. Ideally, we'd be able to do this based solely on physical principles, but ultimately this is incomplete information, and clouds are not the only signal here. We get signal from the atmosphere, the surface, and things like aerosols. So what's commonly done is we'll use a radiant transfer model and wrap it in an optimal estimation scheme. David Lawless gave a great presentation using optimal estimation last semester, but the idea is we can exploit the physics of the radiant transfer model and incorporate things like uncertainty in our measurements and provide a first guess at what we think the cloud properties might be. What's becoming more popular is to use, or more popular recently, is to use machine learning to estimate this, where we have reliable ground truth observations of our cloud properties. So we can train a statistical model to use this information to estimate these properties we care about. What my research focuses on is using neural networks to do this. So we have some motivating questions for this talk. Can we improve cloud property estimation by using neural networks? This should be easy to answer. We're going to train a neural network, compare it to operational methods, see when and where we see improvement. Question 2, how can we interpret neural network predictions and what can we learn from them? If we find that the neural networks outperform the operational methods, it'd be interesting to know what information is most important to the neural network. And how can we ensure these methods are appropriate for climate records? Basically, what considerations do we need to make when we're developing products for climate records compared to operations? And I'll touch on this a little bit throughout the presentation. So the first thing I'm going to talk about is VIIRS neural network cloud detection. The problem of taking 16 moderate resolution VIIRS channels, using that to estimate is there or is there not a cloud in every pixel in that image. Before I talk about that, I'm going to give a very brief primer on what a neural network is. So if you're anything like me, then 4 or 5 years ago you saw a diagram like this at an AMS or AGU conference, and maybe you had no idea what this meant. Maybe you know that information comes in on the left, and we get a prediction somehow, but what do these circles mean? What do the lines mean? Basically, what math happens in between? So to illustrate that, I'm going to start with a very simple example. This is a neural network with one layer, one unit, and no activation function. Some people call these neurons instead of units. I don't think the biological analogy is that helpful, so I just pick the units usually. But we can represent this mathematically, and it's very simple. It's the weight of the first unit of the first layer times the input, x1, plus the bias. So this should look very familiar. So we're going to scale this up. We're going to add an additional input or feature to the model. We're going to add an additional unit to the first layer and a second layer with 1 unit. So again, we can represent this mathematically. The output of the first unit of the first layer is simply the weights of the first unit of the first layer times the inputs plus the bias of the first unit of the first layer. The output of the first unit of the second layer is simply the weights of the first unit of the second layer times the output of the first layer plus the bias. That's very simple. But I'll say that this neural network is already needlessly complex. The reason is this is a linear operation and this is a linear operation. 2 successive linear operations can be represented by just a single linear operation. So in this case, making a deeper model, adding more layers to the model, doesn't help us at all. It doesn't make our model more expressive. And for that, we need nonlinearity incorporated in some way. The way this is most commonly done for neural networks, most neural networks, is by using the rectified linear unit activation function, or ReLU. ReLU is very simple. If we give it a positive value, we don't do anything. If we give it a negative value, we set it equal to 0. So we apply this activation function to the output of every one of these units, and now we've incorporated nonlinearity to our neural network. So you can imagine that if we scale up to a neural network of this size, that this notation gets really messy and annoying. So we use matrix notation instead. And here I've added something new, S. S is the sigmoid activation function. It acts to bound the output of the layer between 0 and 1. That's very useful for estimating something like a probability, like the probability of a cloud being in a pixel. So we would want this on our output. We want our output between 0 and 1. So using these equations, we know how to make a prediction with a neural network. But how do we figure out what the weights are? How do we know what W and B are? For that, we use an algorithm called backpropagation. So the first step in backpropagation is decide on our cost function. This is a function that describes how well our neural network is doing. It compares our predictions to some ground truth that we have. This is just mean absolute error. If we're doing a classification problem, we'll probably use something like negative log likelihood or binary cross entropy. But the cost function is something we want to minimize. And it turns out this can be a difficult optimization problem. The reason is a weights relationship with J, the cost function, depends on every operation between it and the prediction. So what we do typically is we'll randomly initialize the weights. We'll make a first guess at what we think they might be. We make a prediction on a small sample of our data, and we calculate the cost function. And then we compute the derivative of the cost function with respect to the weights. And we adjust the weights according to the direction and magnitude of the derivative. Actually, we adjust it in the opposite of the direction indicated by derivative. So we want to minimize the cost function or maximize it. So those derivatives can be complicated. Looks like this. Turns out it's just chain rule. It's a lot of chain rule, but it's just chain rule. So once we do that, we go back to step 2 and repeat this process over and over again, maybe until the weights stop changing or our cost function stops changing or some other criteria is met. If I lost you on the slide, don't worry. I'm not going to talk about backpropagation ever again, and I'm barely going to talk about neural network training ever again. But at least hopefully you have some vague idea of how we make predictions with a neural network, and maybe a more vague idea of how we arrive at the weights of a neural network.
Chuck, just a quick question. Do you have to invest any time in making your guesses? Can you just make a guess of 0?
There's been some research that some guesses are better than others. Usually we'll use uniform random numbers as we start, because usually we don't have a good idea what we're supposed to be.
Thanks.
Okay, we're going to go back to the problem of neural network cloud detection. So we're going to use 2 instruments for this part of the talk. The first is VIIRS. This is the imager I introduced earlier. The second is Colloquium, the cloud aerosol LiDAR with orthogonal polarization. Colloquium is a spaceborne LiDAR, very sensitive to the presence of optically thin clouds. So it serves as a suitable validation source for many cloud properties, including cloud pressure, cloud detection. We find collocations between these 2 instruments. Looks like this. We use 4 years of observations, which amounts to 15 million collocations between these 2 instruments. We split it up into 3 data sets. First is training. This is what the models fit on. That's how we know what the weights are. Validation. This is what we use to decide on the architecture of our model, like the number of layers, the number of units, what kinds of activation functions we want. And there's a testing data set. This is what we use all the way at the end, after we develop our neural network, to evaluate its performance on unseen data and compare it to other methods we might use. In the first part of this presentation, I'm going to talk about 2 testing data sets, a filtered one and an unfiltered one. Basically, in the unfiltered one, we're removing cloud edges. Those cloud edges are instances where the collocations between these 2 instruments are not exactly correct all the time, but I still want to know what my performance is on cloud edges, so I'll sometimes report results from the unfiltered data set too. Okay, I'm going to talk about 3 different approaches to cloud detection. First is the continuity Modus VIIRS cloud mask. This is essentially an extension of the Modus cloud mask for VIIRS. It's based on physically reasoned cloud tests with high and low confidence thresholds. We have a little bit of uncertainty information from that. But overall, I'd say this is a very interpretable and intuitive cloud mask. When it makes a prediction, it's pretty easy to figure out why. Second is the No Enterprise Cloud Mask, or ECM. It's a naive Bayesian approach, so it's also machine learning. It has cloud tests with a clear physical basis, and it's trained directly with Colloquium, similar to our neural network approach. Third is the neural network. We give it all 16 moderate resolution channels from VIIRS. We give information about the absolute value of latitude, a binary land-water mass. Solar zenith angle, that's the angle the sun makes with the surface normal. Sunlit angle, which tells us where specular reflection of sunlight over water is likely. We give it a 3x3 patch of each one of these inputs, so there's 180 total values given to the neural network for each prediction. Like I said earlier, we train to match variety. There's some details over here about the training architecture of the neural network. This is not that important. I'm not really going to talk about it, but if you want to see it, there it is. Okay, so we're going to look at the performance evaluation of the neural network on the left, VCM in the middle, VCM on the right. We're looking at a quantity here called balanced accuracy. So balanced accuracy differs from regular accuracy in that it penalizes a model for over-predicting the majority class. So if we consider a hypothetical region that has 90% cloud traction, I could make a trivial cloud mask that says everything is a cloud, and it would get 90% accuracy. But its balanced accuracy, which is a function of true positive rate and true negative rate, would be 100% plus 0% over 2. So its balanced accuracy would be 50%. Balanced accuracy is useful, so there's a class response. So back to this. Neural network outperforms both operational models over all surface types we looked at, particularly over sea ice and snow. We can look at the nighttime results, similar story, outperforms all models, especially over sea ice and snow cover. We can look at performance by region. We're looking at the neural network on top, VCM in the middle, VCM on the bottom. We'll look at the difference between the neural network and the two operational models, where red indicates improvement. We see that most improvement is in the middle and high latitudes. We can also look at regular accuracy, since that's sometimes more intuitive for people. And it's a similar story. Most improvement in the middle and high latitudes for both these models. Now we'll look at performance by cloud property. Y-axis here is true positive rate, x-axis is YP cloud top pressure. So we see the neural network in teal here identifies a higher fraction of mid-level clouds, similar performance to the operational models at low levels. We can look with respect to optical depth. We see the neural network more often identifies clouds at all optical depths. We can look at the same results for nighttime, similar story. Okay, all three of these masks are capable of estimating probabilistic output. And in certain cases, there might be value in that. So, say I'm estimating sea surface temperature. I want to be extremely confident that my estimates of SST are reliable. I want to be so confident that maybe I'm willing to throw out some potentially cloud-free observations. So maybe in that case, I want to use a cloud probability threshold of 10%. Say anything above 10% is cloudy and throw it out. It's different from what I was doing before. I was looking at 50%, which is the traditional threshold you would draw in binary classification. What a receiver operator characteristic curve tells us is the true positive rate and the false positive rate for every possible threshold we could draw on cloud probability. This is what those curves look like. This is what it tells us. For a fixed false positive rate, the neural network has a higher true positive rate in pretty much every scenario here. We can look at the unfiltered data set, pretty much the same conclusion. So I'm going to zoom in on the top left here, and then show this for every combination of daytime, nighttime, land, and water for 3 different latitude bands. I'm not going to go through every single plot here, but you can kind of follow a little along and see the neural network has a higher true positive rate for a given fixed false positive rate, particularly over high latitude surfaces. So it seems like our neural network is doing pretty well. From there, I asked what makes the cloud appropriate, or what makes the cloud mask appropriate for climate reference. Of course, we care about performance, but is there something else? So an observation I made over and over and over again in the last few slides is that many cloud masks have detection statistics that vary with surface type. I had this idea that cloud detection ability should depend as much as possible on properties of the cloud and not properties of the surface or solar illumination. So I'll offer a hypothetical to explain why we might think that. So we have 3 surfaces here: land at 280 Kelvin, water at 275, and sea ice at 260. We place a low-level, optically thin, homogeneous cloud over all 3 of these surfaces, and we'll consider the result of 3 hypothetical cloud masks. First cloud mask correctly identifies a cloud for all these surfaces. Second, correctly identifies it over land and water. that maybe struggles over sea ice, says there's no cloud there. Third cloud mass says there's no cloud in this region at all. It's pretty easy to argue cloud mass number 1 is the best, correctly identifies the cloud over all these surface types. But I would argue, depending on the kinds of questions we might be asking, there is reason to prefer number 3 over number 2. For instance, if I'm asking questions about the long-term variability of cloud cover, 10 years from now, there might not be sea ice in this region, and it might be replaced with open ocean. So in that case, cloud mass number 2 would measure a change in mean cloud fraction, even if there was no change in cloud fraction at all, purely due to a change in surface type. Cloud mass number 3 would say, there's no change in cloud cover here. So, how do we quantify something like this? I have one idea that you can take the true positive rate between different conditions for clouds of a fixed optical depth. So what we're looking at here is the true positive rate difference between daytime water, daytime land, and the low latitudes. And what we see is the NVCM has 10% higher true positive rate for daytime water compared to daytime land. The ECM has 10% higher true positive rate over nighttime water compared to nighttime land, and 6 to 7% for optically thick clouds as well. When we go to the higher latitudes, these differences get even greater. We see that both operational models have a true positive rate difference around 25% comparing nighttime water to nighttime land. And you'll see in all 4 of these plots here, the neural network has the lowest, or is tied with the lowest, true positive rate differences. These changes in surface type or solar illumination conditions. So I'll give some context as to what exactly this looks like. So I do a regional comparison using 4,500 VIIRS scenes over Greenland for all 2019. I'm comparing the output of the neural network and the NVCM. I want to emphasize this is cherry-picked. This is the worst case scenario. These are the largest differences we should expect to see between the neural network and the NVCM. Okay. This is mean cloud fraction for all 2019 for the neural network. This is mean cloud fraction for all 2019 for the NVCM. We'll look at the difference between these two. We can see these differences can be quite large, particularly over the Greenland landmass itself, where they can amount to around 30% cloud fraction. So we'll look at a time series of this. We see that the neural network most closely aligns with Calliope. The NVCM looks to be mostly a function of solar zenith interval. So the reason this occurs is that the NVCM has a higher true positive rate over daytime land compared to nighttime land in the high latitudes. So that as such resulted in the NVCM mischaracterizing the seasonal cycle. So the neural network is not perfect, but it's a little bit closer to our true phase set of life. So, main takeaways from this part of the presentation, that neural networks improve upon traditional cloud detection in many ways. Cloud amount analysis from the core regions might be becoming a little bit more realistic if we use a method like this. And there's some evidence to say that neural network might be more appropriate for climate reference. But the broader takeaway is that we need to think about how these products are being used. What questions will we or our users ask? We're asking questions about long-term variability of cloud cover, and to be sure our products is robust to changes in surface type, like the replacement of sea ice with open ocean. Okay, next part of this presentation is going to be about neural network cloud top pressure. Cloud detection was a classification problem. We're estimating the probability of a pixel belonging to either clear sky or cloudy. And it's pretty easy to obtain something that behaves like an uncertainty in that case. It's not exactly an uncertainty, but under certain circumstances we can treat it like one. Cloud top pressure is a regression problem. We're estimating a quantity. And unfortunately, it's not straightforward how we get uncertainty information from that. What some folks have been trying is using an approach called quantile regression to estimate properties of a distribution, like quantiles or percentiles of the distribution rather than the quantity itself. Quantile regression relies on this function here called the check function, where tau is the chosen quantile, so 0.1 is the 10th quantile, 0.9 is the 90th quantile, y hat is our prediction, y is our label. So the implications of this function are that when we're estimating higher quantiles, overestimates are penalized more than underestimates. When we're estimating low quantiles, underestimates are penalized more than overestimates. So I'll give you an illustration of what that looks like. The blue line here, maybe those are observations that we know are true. And the pink line are estimated values from a statistical model, maybe. We see that for these overestimates over here on the right, The check function for the 90th quantile is much larger than the 10th. And these underestimates on the right, you see that the check function for the 10th quantile is much larger than the 90th. So to illustrate this further, we'll make up some fake data here. We fit a linear regression to it. And we'll show the results for quantile regression for 3 different quantiles. We see that the quantile regression gives us information about the conditional distribution, and the distances between the quantiles might give us some information about the uncertainty in our model. So how do we incorporate this into a neural network? It's actually super easy. We specify which quantiles we want. So we're going to choose 9 evenly spaced quantiles between the 10th and the 90th. We change the size of the last layer to match the number of quantiles we're estimating. So you're estimating 9 quantities. Then we modify the loss function. So here, change the notation a little bit. L sub tau is the loss for a specific quantile. The total loss, total cost that we're minimizing, L total is just the sum of the individual losses for each quantile. I'm using loss and cost interchangeably. Okay, here's some details about the neural network that we're training for VIIRS. Not super important. The important thing are the features that we include, the inputs that we include. They are a sparse NWP temperature profile, infrared brightness temperatures from these channels, spatial metrics from those infrared channels, and the VIIRS-CRIS fusion channels. So there's been a few talks on exactly what the fusion channels are in the last few years. Essentially, they are estimates of Modis-like channels using coarse spatial resolution measurements from CRIS mapped to the VIIRS spatial resolution. So CRIS is a hyperspectral sounder. And basically what they've done here is they've created fake channels that don't exist on VIIRS using CRIS measurements and interpolated them to match the high spatial resolution of VIIRS. So if you're interested in exactly how this is done, you can read the paper or you can talk to Dr. Weiss herself. She works in this building. But these top 3 rows here, these are native observations from VIIRS and the associated spatial metrics that I pull out from these channels. All these rows down here with fusion on the front just means they're constructed from a coarse resolution sound. So that's what fusion is. We also train a neural network to estimate cloud top pressure for ABI. Same details over here. Inputs are different. We do not include fusion channels. That's because unfortunately there's no sounder from the GOES satellite. But ABI still makes native measurements in relevant spectral regions anyway, so it will be fine. We're going to jump to the evaluation of the VIIRS cloud top pressure neural network. So what we're looking at here is Calliope cloud top pressure, the y-axis, mean absolute error on the x-axis. And teal is the neural network, and pink is the operational model. What we see is for optically thin clouds, for semi-transparent clouds, and for opaque clouds, the neural network outperforms the operational model at all vertical levels and at all optical depths. We can look at a map of this. Most of the improvement, we're looking at the absolute error here, most of the improvement is at the middle and high latitudes compared to the operational model. We can do this for ABI as well. I didn't do a comparison with the operational model because that's expensive to do, but we see similar results in terms of pressure and optical depth. The spatial pattern of mean absolute error looks very similar to that of VIIRS when you look at the matching regions. So, both these models are capable of estimating distributions of cloud top pressure. This is 3 different ways of evaluating how well we have estimated those distributions. On the right, this is a plot called a probability integral transform. The x-axis is the value of the predicted CDF from the neural network. The y-axis is the frequency of actual observations. So this plot tells us that the predicted distribution in the VIIRS neural network is too narrow because observations disproportionately occur with very low and very high values of the predicted CDF. To contrast that, we can look at the ABI neural network and see that its distributions are fairly well calibrated. I think this information is a little bit more easily shown in this middle plot. The x-axis is the prediction interval. So these are constructed from the predicted quantiles. The 80% prediction interval comes from the 10th and 90th quantiles that we estimate. So ideally, 80% of the observations here should fall in the 80% prediction interval. but we see it's more like 76%. So the predicted distributions from VIIRS are too narrow. For ABI, we see around 79.5% of observations falls in the 80% prediction interval. So again, ABI is better tolerated. I'm not going to talk too much about this last plot here, but it illustrates how as we increase the width of the predicted distribution, the range of errors we typically observe also increases. So that's intuitive. Okay, seems like our cloud top pressure neural networks are doing fairly well. So we might ask what information is most important for their predictions. This is a very difficult question to ask for neural networks because they're composed of several nonlinear successive operations. You can't simply look at the weights of the first unit or the first layer and immediately understand what information is most important, what information a neural network relies on. Also, some information might be conditionally important, based on the characteristics of the temperature profile or observations from other infrared channels. And there's many ways of sort of probing these models, trying to figure out what information is most important. I'm going to talk about a simple one first, called backward selection. So backward selection starts by, we start with all features we might want to include in our model. We train it and we record the performance metric like we just did. Second step is we choose a feature, we remove it, retrain the model without it, record the change in performance, and add that feature back in, and repeat 12 features. After we do that, we permanently remove the feature that increases model error the least. And we go back to 2 and repeat this process over and over again until we run out of features to include in our model. So the idea here is that a large increase in error after we remove a feature from our model implies that that feature has unique information that was also relevant to the task of top pressure estimation. If there was a low error after we removed it, it might mean that feature was not useful, or it might mean its information was redundant among other channels, and the neural network is able to find another way to achieve similar performance. So, this is a plot showing the results of a backward selection performed on groups of features associated with each one of these channels. I'm going to try and break down this plot a little bit. The numbers in this table indicate the increase in mean absolute error after the features associated with each one of these channels are removed. So, Fusion 13.6, when all information from this channel was removed, model error barely changed at all. In fact, it got a little bit better after this information was removed. If we go down and look at 8.6, after information related to 8.6 was removed, model error increased by almost 11 hectopascals. That's a lot. That means 8.5 is really important to cloud top pressure estimation. We'll go to the second round, and this time we're going to test the removal of all features associated with these channels in a model that does not have access to the 13.6. So that's why these numbers are slightly different. And we repeat this process over and over again, and we run out of features. And there's a few interesting things to point out here. First, all the fusion channels are removed before the native observations are even touched. After we remove all the fusion channels, round 7, the mean absolute error of the cloud top pressure model barely changes at all. It increases by about 3 to 4 hectopascals. But as we remove these fusion channels one by one, we see the impact of removing NWP information steadily increases. So there's a trade-off there. Do we want to include information from a coarse resolution sounder, or do we want our model to rely on NWP information quite a bit? It's another interesting thing. After the 13.9 and 14.2 are removed, we see the impact of removing the 8.6 decreases. So to me that indicates there's a potential relationship between the 8.6 and 14.2 that the neural network was using. After 14.2 was removed, the 8.6 got a little less useful. It means the neural network was not able to exploit that relationship anymore. We do a similar thing for ABI. A few different takeaways. NWP information is a lot more important right from the start. We have to strip away some of these less useful channels before we see that the 8.4, 10.3, 12.3, and 13.3 are the most useful channels for ABI cloud top pressure estimation. Okay, both those slides were global explanations. They describe how does the model work on the whole. What information is the most important computed over a large set of features. Here, we're going to be looking at local explanations. The local explanations tell us how much a feature contributes to an individual prediction. We're going to use two methods to show this. First is layer-wise relevance propagation, or LRP. I think it was 3 or 4 years ago, Dr. Elizabeth Barnes from Colorado State University gave a talk here where she used layer-wise relevance propagation to understand predictions made by a neural network. I'm also going to use Shapley additive explanations, or SHAP. So I'm not going to explain in detail about how either of these methods work, because that takes a really long time to do. The important thing to know is that both these methods allow us to attribute responsibility for a single prediction made by a neural network and understand which features, which inputs to the model were most important for that prediction. This is an example of what that looks like. So, top panel here is the VIIRS 11 micron channel. Below that, predicted cloud top pressure from our neural network. And below that is the width of 80% prediction interval. So this can be loosely interpreted to be an uncertainty in cloud top pressure estimation. These 5 panels here are the relative feature importance imparted by layer-wise relevance propagation for 5 different conceptually linked groups of features. So those groups are NWP information, brightness temperatures from the native observations from VIIRS, brightness temperatures from fusion channels, and the spatial metrics from both. There's a lot to pick out here. I want to point out one thing. Brightness temperatures from native observations are most important for upper-level clouds. They are profoundly unimportant for cloud edges. For cloud edges, spatial metrics are most important. That makes a lot of sense, because the brightness temperature for the cloud edge is, the interpretation is a little ambiguous. It's a function of clear sky radiance and cloudy radiance. The spatial metrics might be indicating to the model that this is a situation where this is happening. The neural network is able to adjust accordingly or increase the width of the predicted distribution, saying this is an uncertain prediction. Okay, both those methods produce attribution for each feature for every example. I said that like 4 times. That's a lot of information. That's 51 values for every single prediction. That's too much for me to parse, so I tried to simplify it. I applied a k-means clustering, not to the features, but to the attributions to those features. So the idea is, I'm trying to organize these into more similar explanations on these groups and compare differences between the clusters that I found. Okay, a lot of information. I'm going to try and break this down a little bit. At the top, we're looking at the relative feature importance, the distribution of relative feature importance for each feature in each of these 4 clusters that I identified in the attributions. Cluster number 1 has high feature importance in 8.6 and 10.8. We see that cluster number 1 most frequently explains optically thin clouds at all levels, represented by the dashed line. We see that cluster number 1 is frequent globally, but most frequent in Antarctica. We can go back. We'll look at cluster 3 this time in white. Cluster 3 has high importance in the 13.3 fusion channel, high importance in some spatial metrics associated with the 12 micron, also high importance in NWP surface temperature. Cluster number 3 explains large fraction of low-level, optically thick liquid clouds. And it is frequent in regions where we see persistent low-level cloudiness. We do something similar with ABI. We'll look at cluster 2. It has high feature importance in the 12.3 micron channel, high feature importance in the UV surface temperature. It explains large fraction of low-level liquid clouds, occurs mostly in the tropics. We'll look at cluster 4 in yellow. It has high importance in channels with strong water vapor absorption, as well as 300 hectopascal in UV temperatures. It explains a large fraction of opaque ice clouds between 200 and 600, and also upper-level liquid clouds. It occurs mostly in high and low latitudes. So I wouldn't take anything specific away from this, but we can tell that the neural network is learning different strategies, relying on different sets of features, depending on key cloud properties like opacity, phase, cloud top pressure, and location. Okay, we're going to step back and look at global attributions from both of these methods, simply just averaging over all the predictions that we made. I'm not going to talk about differences between these two methods, because that requires a long explanation of how they both work. But I'll point out a few things. 8.6 is the most important, followed by 10.8, 12, and 13.3. Spectral information, much more important than spatial information. Spatial information is more important than NWP information. We go over ADI. 8.5, very important, followed by 11.2, 12.3, and 13.3. Again, spectral is more important than spatial. Spatial is more important than NWP data. Last thing I'll point out is that the ozone channel on both these sensors almost useless for cloud top pressure estimation. Okay, main takeaways from this part of the talk. Machine learning interpretability methods offer a variety of perspectives with many caveats. Despite those caveats, there's a few concrete takeaways. 8.4 is by far the most important channel for cloud top pressure estimation. That makes a lot of sense. The index of refraction for ice and water clouds is very similar to 8.4. So the longer wavelengths, like 10 to 13, the index of refraction between ice and water clouds is more different. So if we use 8.4 in conjunction with something like 12 microns, we can get information about cloud phase. Once we know cloud phase, we can narrow down the range of cloud top pressure estimates to the upper or lower troposphere. I say that 10 to 13 microns plays a moderate role because we have lots of information in those, often several channels in this range, so the feature importance is shared between them in this case. We learned that neural networks learn variability related to key cloud properties like opacity and phase, complicate cloud top pressure estimation. We saw that from the clustering analysis. We didn't talk about this too much, but VIIRS and ABI neural networks have some similarities. We saw a cluster that was similar between them, but overall they do not have consistent explanations. This is because they include different features. They're trained on different data, and VIIRS views a much wider range of meteorological conditions compared to ABI. And finally, just as a reminder, if interpretability was a primary concern, we probably shouldn't be using neural networks to begin with. We should probably be using something more simple. In this case, we're interested in interpretability because the neural networks perform so well. So we're trying to understand what information is most important. And it's mostly 8.4, 10 to 13 microns, and spatial metrics in key scenarios. Okay, last part of this talk. So, if you're anything like me, when you see results from the cloud top pressure model, the cloud detection model, you might say, okay, let's run this on a lot of data. Let's run this on a climate record and see what new things we might learn compared to the older methods. But I would argue there's a different set of considerations, like I talked about earlier, when we're developing for climate records versus operations. And the big one is intersensor consistency. The reason we need to think about intersensor consistency is that our longest observational records look like this. In the case of AVHR, where we have to stitch together observations from multiple different satellites in order to have a record long enough to do anything with. Geostationary record looks even worse. It looks like that. So unless we address this in a very intentional way, we're limited in the kinds of questions that we can ask, kinds of analysis that we can do on our longest observational records of clouds. So I would argue this is a key challenge in transitioning machine learning algorithms to climate records, because we often train our algorithms on just a single sensor. In this part of the talk, I'm going to consider the simpler case of VIIRS and MODIS intersensor consistency. So these are two imagers with similar equatorial crossing time. They have a vaguely similar subset of infrared channels used for cloud top pressure estimation, but there's still some challenges. The spectral response function of those similar channels do not match exactly. The spatial resolution of these two images is also different. So our goal is, sorry, it's at the bottom, we want neural networks trained to estimate cloud top pressure for VIIRS and MODIS to agree when they see the same cloud. If they don't agree, that means there's going to be serious issues in whatever climate analysis we do afterwards. So I'll talk about the data that I collect to sort of address this. Quantile is still our labeled data set. First data set we actually collect is a collection of MODIS and Colloquium observations. So MODIS is the image of background, Colloquium is footprints on top. Second data set is VIIRS and Colloquium. It's very similar. Third data set is a little bit different. Ray-matched collocations between MODIS and VIIRS. So a ray-matched collocation is an instance where two imagers have observed the same path in the atmosphere. That's important because radiation doesn't just come from a point source on top of a cloud. It comes from within the cloud. It comes from the atmosphere above and below the cloud. It comes from the surface as well. So if we're looking for instances where these two imagers see the same thing, the situation on the right here is much preferable to the one on the left. This animation over here is two approximately ray match scenes between Lotus and VIIRS. Okay, this is the geographic distribution of all three data sets we use. Train, validation, testing. From top to bottom, it's VIIRS and Calliope, Lotus and Calliope, and the bottom is Lotus and VIIRS. So the bottom row is not what I would call globally representative. And I'll talk about that a little bit later. Okay, our proposed approach to train sensor-specific, fully connected layers for each sensor. Feed those representations into shared layers between both sensors, where we get our eventual cloud top pressure prediction. This neural network is trained with this loss function, where L VIIRS Calliope is the absolute error between the prediction made on VIIRS features minus the corresponding Calliope label. L Lotus Calliope is a similar interpretation. The important part is LC. This is what I call the consistency loss. It has two components. The first component, differences in predictions for VIIRS and Lotus when they see the same cloud. That comes from the ray match collocations. The second component, differences in intermediate representations extracted from the last sensor-specific fully connected layer. So, the motivation behind this is that we want the neural network to obtain similar intermediate representations from these slightly different feature sets. We want to ensure that these representations are similar enough that they result in low differences in predictions between VIIRS and Lotus. Last part, off the C, the constant describes how much this contributes to the overall loss. So, if I lost you on this slide, maybe I lost one person on this. VIIRS and Lotus observations differ very slightly. So what we're doing, we're adding a loss in terms of a loss function that minimizes differences in predictions when these two sensors see the same cloud. Okay, in order to know whether or not an approach does anything, we need some baselines. First baseline is one neural network trained with VIIRS and Calliope. In that case, we're assuming that VIIRS and Lotus data are interchangeable and that we can use the same model for both sensors. Second baseline, two neural networks trained independently on their respective collocations with VIIRS with Calliope. So in that case, we're sort of crossing our fingers and hoping that those two models that are made from these collocations with Calliope are consistent with each other when they see the same cloud. The third baseline is a conventional baseline. This is the operational cloud-prop VIIRS Lotus cloud-top pressure product. It's based on, or uses optimal estimation, so it takes into account the specific spectral response function of the channels on each instrument, and it's effectively the same as the NOAA operational product. So if you've seen that before, then you've seen this. Okay, so we're going to look at the evaluation of these four different approaches, first with respect to Calliope, and then the intersensor consistency between VIIRS and Lotus. We're looking at the operational model here. We see that compared to Calliope on VIIRS, it does just okay. On Lotus, it does just okay, with mean absolute errors above 100 hectopascals. But its intersensor consistency is pretty good, around 28 hectopascals. We look at the one model neural network baseline. It does fantastic on VIIRS, it does great on Lotus, but its intersensor consistency is really bad, about 60 hectopascals. So we'll look at the two model baseline. Again, great on VIIRS, even better on Lotus, but its intersensor consistency still does not come close to the operational product. So we'll look at our proposed approach with the consistency loss. You see that performance is still pretty good on VIIRS, still pretty good on Lotus, but if we increase the consistency loss rate high enough, that's alpha, then we can outperform even the operational product in terms of intersensor consistency. So, we can also do this with only minimal sacrifice in performance if we choose something like alpha C equals 2. So, this confirms that our approach works. We're able to improve upon the intersensor consistency of a neural network cloud-top pressure product between VIIRS and Lotus. But there's a problem with this analysis. It's right here. This is done on the Ray-matched data set. It's not globally representative. So to address that, collected 3 years of VIIRS and OS observations, 4 different regions that are not well represented in our previous testing data set. What we'll do is we'll calculate a metric called Earth Movers Distance for 28 composites, 28 composite PDFs of cloud top pressure. So Earth Movers Distance is a metric that we can use to compare 2 different distributions. A low EMD means 2 PDFs are very similar. High EMD means they are very different. So we want our low EMD values, that means low differences in predicted cloud top pressure distributions for these 28 composites. We'll look at the first 2 regions. We see that our proposed approach with the consistency loss has the lowest EMD values throughout this time series. We look at a third region. This is off the coast of California. We see our proposed approach is comparable to the operational model, but the 2 neural network baselines have issues with seasonality. We'll look at the last region. This is in the North Sea. We see our proposed approach has the lowest EMD values throughout. All 3 approaches have small to large seasonality. So this confirms that our approach works outside of our geographically limited testing data set. Sure.
Can you remind me the alpha you're using on those?
Alpha equals 2. But I recognize that Earth Movers Distance is not really a physically intuitive quantity, so I reframe this analysis in terms of variables we might actually use in trend analysis, like high, middle, and low cloud fraction. And what we're looking at here are the differences in these quantities between VIIRS and MODIS. So as you look across, you see that our proposed approach typically has the lowest differences in high, middle, and low cloud fraction, especially compared to the operational model, which seems to struggle with high and low cloud fraction and copies. So this confirms that low EMD values translate to low differences in quantities that we care about. Here, I have a question. How does it actually change the neural network itself? We know how it changes the output, but for instance, how does it change feature importance? So what I did was I used layer-wise relevance propagation again to determine the relative importance of the features. Features included in this model were sparse NWD temperature profile, spatial metrics derived from the infrared channels, and the infrared channels themselves. And we're looking at the relative feature importance over several model runs, comparing the 2 model neural network baseline to our proposed approach to the consistency loss. What we see is when we add the consistency loss, there is an increase in the usage of NWD data. That makes sense. NWD data is the same regardless of the sensor. We see a general decrease in the usage of spatial metrics. Again, that makes sense because the spatial resolution between both these sensors is different. But we see some unintuitive changes in the importance of particular channels. Specifically, a decrease in 8.6, a decrease in 10.8, and an increase in 12. I say that's unintuitive because the spectral response function of the 8.5 is actually more similar between the 2 instruments, and 10.8 and 12 are actually a little bit more different. So while our approach works, it improves the intersensor consistency of a cloud top pressure product for VIIRS and MODIS. It's changed the relative feature importance in some unintuitive ways. It's unintuitive. Okay. Main takeaways. If we care about intersensor consistency, we can't assume that MODIS and VIIRS data are interchangeable. But we can improve intersensor consistency if we add a term to the loss function that minimizes differences when they see the same cloud. We can do this with only a small change in performance with respect to colliding. So we're gaining a lot in terms of intersensor consistency, losing very little in terms of performance. I didn't have time to show this here, but in our paper we show that we can accomplish this when only one sensor has labeled data for colliding in a supervised setting, and when each sensor utilizes a different set of channels. Okay, main summary. Can we improve cloud property estimation by using neural networks? Yes. How can we interpret neural network predictions and what we can learn from them? Well, it's complicated. There's a wide variety of methods, mostly limited takeaways from each one of them. Current tools disagree. It's not clear which one is correct. And to top it all off, feature importance doesn't necessarily imply physical significance. Despite that, there's a few takeaways that we can be confident in, and that we have physical explanations for, like 8.4, the infrared window channels, and spatial ranges. How can we ensure these methods are appropriate for chronometers? It's a tough one. I think the best thing we can do are quantify the characteristics of our product that we care about, and use those in our evaluation, focus our evaluation around them, or even optimize for them, like I did in the last part of this presentation. But unfortunately, the relevant metrics and solutions are likely unique to each problem. I can't use TPR differences for contact pressure. Not every pair of imagers has ray-matched collocations between each other. So the solutions are probably unique for each problem. So, I'm done. I will stop there, and I will answer any questions if we have time. Thanks.
So we have some time for some questions for folks who want to ask something?
Yeah, go ahead.
So I've got a bunch, but I'll save some for later. But for now, just as a purely mechanical, practical issue, if I did the multiplication right, your network, the one you described at the beginning, has something like almost 1 trillion weights. If you just multiply the number of nodes in each layer together, it's a very large number of weights, and maybe I miscalculated, but that would be an enormous number of weights to train and would imply pretty big hardware demands and training times and all that. Am I miscalculating what that looks like?
This one?
Yeah, I mean, I started with what you had in your thesis, with like 200 times 100 times 50 times 25 times 1. Maybe I had an extra 200 in there by mistake or something. But I guess in short, could you comment a little bit on the practical aspects of running this model? Are you using GPUs? Are you does it have to train for a long time to get convergence?
Yeah, so the parameters are not in the trillions for this. It's something like 15,000, if I remember correctly. So we might, I don't remember the math off the top of my head, but we might be doing that a little bit incorrectly. These are all fully connected neural networks. And there are not many operations in a fully connected neural network compared to like a typical convolutional neural network. So for these neural networks, we could probably train them on a CPU. I did them on a GPU because it was about 4 to 5 times faster. But typically this neural network was trained in, I want to say, under 10 minutes on a GPU.
Okay, thank you.
There is a question online. Stephen Miller says, nice job, Chuck. Early on, you showed statistical improvement over high latitudes. Did you look at any anecdotal cases to show exactly how the cloud detection changed for representative scenes?
Yeah, I looked at a few examples. Mostly it was low-level warm clouds over cold surfaces, particularly over Greenland, where we saw improvement. So to me, that means Arctic inversions are probably a scenario where the neural network could outperform the two operational models. The neural network actually has for cloud detection, has no information on the temperature profile and no information on the surface temperature either. I think I hid the slide here. Maybe I'll unhide it and show it real quick. This was a surprising result for us. So basically, I thought for certain, one region where the neural network would be worse would be when there's low thermal contrast with the surface because it doesn't have access to surface temperature. But if we look at the accuracy, if we look at the accuracy of the neural network, specifically over where we expect low thermal contrast, it actually does a lot better than the two operational models. So it's a mystery to me as to why. I guess it's more efficiently exploiting multispectral relationships that just weren't baked into the ECM or NVCM. But yeah, certainly a specific case where we see improvement from the neural network would be Arctic inversions.
But that's a challenge for the so-called physical approach, like the motors, right? Because you're assuming the cloud's going to be colder, so
Yep.
you're going to get it wrong.
Brad.
towards the end, you showed that the 11 micron, the dirty window channel, was more important for consistency, even though it had than 8.6. Is there
Yes.
something in the MODIS spectral response function that is capturing some surface property that introduces that sensitivity, or is there, they have different bandwidths, right?
Yeah, so,
Is there anything in there that's sensitive, it's a dirty window channel, is it sensitive to surface property?
right, so we specifically see decreases in the 10.8 and 8.6, and an increase in 12 for both sensors. And this right here in the yellow is the 12 that we see the increase in. So yeah, I think they're definitely measuring slightly different things. But the reason why this was unintuitive is because they measure slightly different things. And judging just purely from the spectral response functions, this is why this is unintuitive to me. Because we see a decrease in usage of this channel that to me looks very similar in terms of the spectral response function. But we see an increase in the one that looks particularly different. So I think you're right. I think there may be some physical aspect of the atmosphere of the surface that, well, actually, I don't know. That's a good question. Why we would see an increase in the usage of a channel that has a different spectral response function.
Any other questions? Yeah.
Your truth for the model, like what you're comparing to is VIIRS, right?
The truth for all these models comes from Colloquium. The features we're using to predict come from VIIRS, usually.
Okay. I was kind of wondering to what extent would uncertainty and quantity maybe propagate into your model, or if you have any ways that you use to look at some of the uncertainty associated with some of the base inputs and truth data for the model.
Yeah, so that's the big question, right? Calliope is one of the most globally representative, best observations of clouds that we have. So if we train a neural network to match Calliope, we're just training a neural network to match whatever Calliope says, and whatever issues Calliope has are going to propagate into our neural network. So we actually see that pretty frequently around, I didn't talk about this at all, but for low-level boundary layer cumulus, where Calliope is not great, and particularly where the co-location procedure between VIIRS and Calliope is not great, we typically see some issues from the neural network, more than the operational models. So yeah, it's an issue of both characterizing the performance of the models, and since we're trained directly to Calliope, it's baked in further into this analysis for low-level boundary layer clouds that have issues with co-location and issues from Calliope itself.
Any other further questions online? No? Okay, well, I guess let's give another. I guess this concludes, and the committee will meet soon. Thank you.
Here?